Okay, so let's start up part 2, and what we're going to do is model those secondary beams that cut across these primary beams. The first thing we need to do is find the height, find the location of where we're going to start those, and we know that we need this to rest up at the top of these beams, but probably with a bit of an offset so that we don't have any collisions due to the curvature, right? It's kind of how we modeled it before. So let's start with the offsetting. And I'm just going to move this up a little bit so that's not in the way. Okay. The other thing I'm going to do is I'm going to double click on the chain here. I'm going to add a little relay because that'll keep my script nice and clean, and you'll see that in just a second. All right, I'm going to go to curve, and I'm going to find the offset. Let's see, where is it? Utilities probably. Yes, offset curve. The curves that we're offsetting are here. And by default, you can see what's happening. Some of them are going up, some of them are going down. This is because we haven't set the offset plane, and by default, Rhino is trying to figure out the best plane for this, which it gets wrong pretty often. So I'm going to go to vector, and in this case, we need a plane to be in the, I think it's the YZ plane. So grab a YZ plane and add that there. And now you'll notice that all of them, in this case, are going downward. Which is not a problem. All we need to do is reverse this D input here as 1. So what I'm going to do is right click on D, go to my expression again. Due to my double screen, it's going to, hang on a sec, let's do this. D expression, there it is. And then just type in -x. And now they're going now upward. So we reverse that, that direction, no problem. And the next thing we want to be able to do is to customize this D input, and we want it to be related to the height of the beam, so that when we do our offsetting, it rests just up at the top. So if I change this value, the offset will update. So I'm going to go back into my math tab here, and I'm going to grab my multiplier, so multiplication, and I'm going to multiply the height of this thing by 2. Okay, so I'm going to grab another panel. That. And that'll give us the overall height. And then I'm going to add a little bit of an offset, like a little bit of a gap, like we did before. So I'm going to go back to math, and I'm just going to add a value to this, and this is going to become a new parameter for us. So I'm going to copy and paste that and just plug it in here, and I guess I'll put that to 1 for now. This is not something that we'll ever really want to change, this one here, so I'm going to just nest that in and just place those in a place where I don't care. And then, but this one is something that we'll want to update later. So I'm going to label that as the kind of gap between primary and secondary, and that's currently is in the wrong unit. It's currently at 1 foot, so we have to divide this by 12. So you can just copy and paste these two things, the divider if you like, and then swap out that input like this, and we're going to plug that into our D input here. Okay, it looks like I may have chosen the wrong one, so I'm going to, because that seems a bit high, so I'm going to try, instead of the 9, I'll put in the 6. Okay, that seems to be a bit better. And you can see now that our offset, it's got a nice little gap. I can change this to 0.5 or something to make that a little smaller. And our gap is, our little offset looks pretty good at about there. You can experiment with this after you draw the beams to ensure that they don't intersect. I'm going to leave it at 1 just because it's a nice round number. Okay. So we have our offsets. And now that we have a line that we can use to locate the secondary, the start at least, starting and end points of the secondary beam structure, we need to divide these into how many beams that we want to go across. Okay, so we're going to do that again. So we're going to go to curve, division, divide curve, plug that in. Looks like by default we're set to 10 here. I'm gonna just update that to keep it custom. So I'm gonna grab another panel. Let's make it 12 instead, something like this. And this is going to be another parameter that we're going to want to pay attention to, because this determines how many, basically how many sets, how many beams are going across, how many, what's the number of the set that goes across. So let's make this number of secondary beams. All right. And if you remember, we didn't have a beam right at the end point here, because that doesn't make a lot of sense. We want to bring the secondary beams inward and let these continue past. It's a better way to end the structure in this case, because you can't really connect something with dimension to the end point of something. You'd have to pull that in a little bit, and we're not going to fuss with that dimension. So we're just going to remove this set of points and the other set on this side from this set overall. So to do that, because it's the first and last in line, it's quite simple. We can just go to set, sequence, call index, and culling is removal. We're going to plug our P into the L here, and then we're going to need a couple of panels, at least just one actually. We already have one panel here. The other one you want to put in 0 as the input there. And I'm going to plug in 0 first into the I. As you can see, we've removed, now if I make that selection, we've removed this point from that. And then I'm going to hold shift, and as I hold shift, I'm going to plug in the 12 that we used as the divide into there. And that should have, yep, okay, so that got rid of our last set down here, because that's the 12th index of our overall set of 13 points. The reason why that works without having to subtract 1 from this number is because this divide component will give you one more point than you have the number here, because actually what this is doing is making a number of segments between the points, not the number of points. Hopefully that makes some sense. Okay, I'm going to turn that preview off. These are now the points that I'm going to use to start drawing lines across that will become rails. So let's try that out. So let's go to curve, spline, interpolate, plug that in. We have the same problem we had before. So all we need to do is go to set, tree, flip matrix. Let's flip that matrix and do this. So now we've drawn a cross. And those are the rails. So this next part gets a little bit tricky, and I'll try to take this one slightly slower. What we need to do now is orient a plane at all of these points that's not only perpendicular to the curve, but also aligned with the normal that comes off the surface that would form our overall structure, our overall architecture structure. So we actually need to draw a construction surface, and we need to draw perpendicular frames. And then we got to bring those two things together to make a newly aligned frame in order to do the sweep properly all the way across. We did do this before manually, and it took a very long time. Each one of these we needed the normal, and then we needed the offset, and we had to do, I think, not only a rotate, I think once, but also maybe twice, if I remember correctly. So it is basically a two-axis rotation that is required to get those planes correct. Okay, so let's get started. Let's first find the normal direction, because we know we need it. Okay, so we're going to find that normal direction by drawing a construction surface through the set of points that the set of curves that we just drew here. So we'll go to surface, loft, which is here. Surface, freeform, loft. And we'll plug in our curves into here, and nothing's going to happen just yet. We actually need these to have a different kind of data structure. So what we can do is just right click on that C and click flatten, and that will turn it back into being a single list, which we can now draw our surface through those curves like this. We don't need to see that surface, so I'm just going to go right ahead and turn off that preview before we get too far. And now those of you in Rhino 5 can go ahead and follow these directions, and those of you in Rhino 6 can also do this. It's just a little bit longer, but if you remember, Rhino 6 has a shorter version, and you can go ahead and do that if you like, if you know how. Because what we need a little more information from the points and relative to the surface. We need the normal direction from the surface that's created when we draw out this kind of structure. So let's go to surface analysis, surface closest point, and let's also, while we're still here, go to analysis again and find the evaluate surface, which is here down at the bottom. So we're going to pull those points to be closer. And those points are the flipped matrix here, the called matrix. So we're going to bring the D output out of flip into the point input of surface closest, and the surface is the loft, like this. So those points are going to appear to repeat. That's fine, but now we have this output here, which is the UV, which is what we need. So we can plug that surface into here, and the UV value is UVP there. And you'll see a whole range of planes being drawn along that surface. If it's drawn correctly, you can see that they're all oriented properly. And we can turn off the preview here because really all we needed was that normal direction, which is coming out there. And in order to visualize that, I can show you a way to do that just to make sure things are working well. You can go to display, vector display all the way to the right under the vector panel. And the anchor for each one of these vectors is the point that comes out of that component, and then the normal will go into the V input, and you can see that a bunch of arrows are being drawn. In my case, they're going downward, and that's just because the surface itself is flipped, has a kind of a top face of being that's downward facing at the moment. This will not affect the next step, so we don't have to change it. But if you wanted to, you could flip the surface and get those arrows to work in the proper direction. But like I said, it won't affect this step. And we're only going to use that normal as an alignment direction. Then the next thing we want to do is similar to what we did in the previous part, which is to find a perpendicular frame at all these points. But we're going to need a little bit more information from this set of points here, because this is just points. We actually need a T parameter, because we're not going to use a slider for that because we've got a whole set of them now down the line. So let's go to curve analysis, and you should be able to find curve closest point, which is just here on the left. So the points are going to be the D output coming out of flip, and the curves are the curves that we drew through those points. And we're going to pull those to it. And something similar is going to happen where you don't really see much of a change. Actually, we can leave those curves on. But what we do now have is this T parameter that we'll use in the next step. So while we're still in curve, go to analysis again and find the perpendicular frame component like we did before. The curves that we're drawing against are the long rails, and the T parameters are there. And these are going to look like they're, some of these are going to look like they're rotated right, some of them aren't. And I can't explain that, but it's not going to affect our process here, because we're going to realign them anyway using the normals that we just drew from the previous step. So we're going to do that with the align plane component. So go over to Vector tab, and there's a plane panel here. Under the plane panel, you'll find the align plane component, as you can see there. And the plane that we're trying to align is the one we just drew, so that goes into P. And the normal is what we're going to use to align it. So turn off the preview for the previous plane, and only show the preview for the aligned ones, and you can see that they now are drawn nicely along the curve perpendicular, but if we look more carefully, they're also oriented in space normal to the surface. So they deviate a little bit in that axis from the curve, from this long curve going in the short direction, the cross section, but they're perpendicular to the longitudinal direction and to the surface at the same time. You remember how manually tedious this was when we did the Rhino version of this. Okay, so now we can draw our cross section along all those planes. So we'll go to curve again, primitive, rectangle. Planes are here, and we can turn those planes off because they get a little distracting. And we can go back to what we did before to do a little copying and pasting. We'll probably save some time that way. So I'm just going to take these three things here, copy those, right? So and then just bring those over like this. I'm going to make a set of, actually I only need one. I only need to do this once because this is going to be a square cross section, so I can repeat that into both inputs of x and y. And then the last thing we need to do is make a domain of this, so we can go to math, construct the domain, right click on A again like we did before, set the expression to -x, and go ahead and plug that in. And then we're going to change this value, in my case of 9, to something like 3 to make that a 6x6 beam. And I'm going to plug that domain both into x and y. And if we zoom in, you can see that we've drawn our cross sections at that size. Last step is to just do the sweep. So go to surface, freeform, sweep 1. The rails are the curves. And I think, just to clean up the script a little bit, I'm going to pull this up a little, pull that down and out of the way like that. And then I'm going to be able to just kind of draw that right through. This way we don't get a lot of overlapping lines. It starts to look a little squiggly. And then our cross sections are the rectangles that we just drew. And let's have a look at what that output is. That looks pretty good. Oops. Now these are going to twist a bit. We're not going through the process that we went through exactly before, which was to, take this, let's say for example that one, and extrude that straight across, and then start with this one and go straight across, so that there was a little rotation and a little gap in between each. For the purposes of this exercise, that's not necessary. But what we have shown is how to really quickly orient a whole array of cross-section curves along a complex shape, so that your sweep at least can be consistent in every cross-section all the way across down the line, which means the square itself doesn't change proportion, but it does twist a little bit. So that looks pretty good. And just to wrap up part 2 here, what I'm going to do is add a custom preview on this like we did last time. And before I actually do that, I'm just going to cap this because these are all open. So I'm going to double click. I don't remember exactly where this is, so I'm going to double click on the gray, type in cap. You'll find the cap holes component, and that'll cap all of your sweeps. You can do that also with the primary beams from the last step as well if you like. Turn off the preview of the sweep because otherwise it starts to overlap. And then head back into display, grab your custom preview, go back to parameter, grab your color swatch, and give it a color. I'm going to give mine I guess a light bluish tint, something like this maybe. In order to really visualize that right though, I got to turn off that preview. And I'm going to, yeah, I think that looks fine. Okay, that's it for part 2.